Lucas?
Yeah, sorry, I don't know, it said I had to download some kind of update.
Yeah, I think GoToMeeting upgraded their program a couple days ago, so that makes...
Yeah, sorry about that.
That's all right. So what are we going to do today?
We were primarily doing synthetic division in class recently.
Okay.
So, I don't know, if problems
Do you have
about
a
that.
synthetic division problem that we can do just to review it?
Let me see. I don't know where it is in my book, because we haven't done, wait. Done. I don't know where they are in my book.
Well, it's difficult to make up a synthetic division problem because I kind of need a cubic function with one solution known. Here, let me check my database, see if I have any synthetic division problems. Don't.
And we were doing rational roots and synthetic division.
Right. Unfortunately, I don't have my stuff categorized by that. Yeah, so it'd be nice if I had all my materials categorized by subject matter, but I don't. So I don't have a database of synthetic division problems.
All right. Where? I suppose it would be in the index of this book. Yeah.
Yeah. Look in the index and look for synthetic division.
All right.
Now we have the same book. Is that right? We're just different.
I have the 7th edition.
And I have the 5th. Okay. Well, let me look in my book also.
So it says here it's on page C17.
Sure.
In my book.
Synthetic division of polynomials on mine is 202.
All right.
All right. You have some problems?
Yeah.
Okay.
X cubed minus 5x squared plus 3x minus 2 divided by x plus 1.
All right. We could do that long division.
Yeah.
Do you know how to do it long division?
Yeah.
Okay.
I actually don't know how to do synthetic division very well.
When you do synthetic division, you take the solution. What is the solution if that is a linear factor?
-1.
-1, exactly. So we put the -1 inside the box. We put the coefficients across the top. And we have to allow for a spot for every degree of x. In other words, if the 3x squared wasn't there, I would need to put a 0 in right there for 3.
Yeah.
Okay, but since we have an x cubed, an x squared, an x, and a number, I can do it like this. Okay, so that's the way you start. Draw a line. First step is you bring down the 1, always. Bring down whatever that number is. Next step is to multiply that by that and put it there, and then add and repeat. Add -5 to -1, you get -6. Multiply -1 times -6, I get 6. Add 3 to 6, I get 9. Multiply -1 by 9, I get -9. Add those two numbers, I get -11. Now, the fact, there's something called the zero remainder theorem. If x plus 1 was a factor of that cubic, this remainder would have to be 0.
Yeah.
If that remainder is anything other than 0, then this is not a factor of that cubic. And that's a huge theory in math, is the zero factor theory, the zero remainder theorem. And since we just did this, unless I made a mistake, I don't think I did, -6 plus 6, 9, -9, -11. Yeah, no, it's x plus 1 is not a factor of that cubic polynomial.
Yeah.
Now, what's interesting is that what I have on the bottom is the remaining quadratic. In other words, that's x squared minus 6x plus 9. So if I divide x plus 1 into this, I'm going to get x squared minus 6x plus 9 with a remainder of -11, which means -11 divided by x plus 1. So that would technically be my answer. When I divide that cubic by that linear factor, I get that.
Yeah.
All right, you got another one?
2x to the 4th minus 5x cubed plus 7x squared minus 3x plus 1.
What do we do?
Divided by x minus 3.
Okay. So what do we put in the box?
3.
And our coefficients are 2 minus 5, 7, 3, and 1. Okay. Tell me everything that goes here. What goes here?
The 2.
What goes here?
6.
What goes here?
1.
Here?
3.
Here?
And
Here?
30. 33. 99. 100.
That means that is not a factor of that. So, if I divide x minus 3 into that, what is my answer?
It's 2x cubed minus, or no, plus x squared, plus 10x plus 33 with the remainder of 100.
And the remainder of 100 means this. It's the remainder of 100 divided by x minus 3. Now, Have you had upper and lower bounds yet?
I don't think so.
All right. Because whenever you divide by a certain factor, if you get all positive numbers, it actually means something. It means that that is an upper bound. In other words, there is no solution greater than 3 to this problem.
Yeah.
Okay, what else you got?
9x cubed plus 7x squared minus 3x divided by x minus 10.
No constant?
No constant.
Okay. So what goes in the
So
box?
10, 9, 8, 0.
Goes here.
9, 90, 90.
These are strange problems they're giving you.
Yeah.
Very strange problems.
I don't know what's up with this.
No, I don't either. These aren't the kind of problems I typically see. In other words, typically, they're giving you a solution to the cubic, and they're trying to get you to prove that that is a solution. And it usually is in the problems, and this has to be 0. In other words, I'm not sure what the point of doing these exercises is, dividing that into that, when we keep getting a remainder. I mean, it gives us practice on synthetic division, but it doesn't really give us much insight into the nature of the problems. Let me give you one. Let's just do it so that we'll see how this is supposed to work. These problems you're giving me don't really shed much light. Okay, if I divide this by x plus 4, I'm going to put a minus 4 there, 3 there, 7 there, minus 20 there. Now, if I want to know if this is a solution, one of the factors of that quadratic, then I must get a 0 right there. And I do. What's the other factor?
The other factor is 3x minus 5.
Yeah. In other words, if I were to multiply x plus 4 times 3x minus 5, I would get 3x squared. Then I have minus 5x plus 12x, that's plus 7x, minus 20.
Yeah, and then with cubics, you do synthetic division, or you find the rational root.
Well, that's a different problem altogether. In other words, rational factor theorem. Quadratics are easy. There is no quadratic you can't factor. All you have to do is, if you can't factor it, then you call upon the quadratic formula, right?
Yeah.
That always gives you a solution. Well, not so with cubics or quartics or anything higher. If I give you a problem like this, finding the solution is no easy matter.
No.
And there's something called the rational factor theorem that says, now we know there's 3 solutions to that because it's a cubic. Quartics have 4 solutions, quintics have 5 solutions, and so forth. The rational factor theorem says that if one of the zeros is rational, You know what rational means, right? As opposed to irrational?
Like a real number?
No, not quite. Rational means it can be a fraction. That's a rational number. That is not.
Oh,
That
like
is not.
too.
That is not. In other words, I cannot write any of these numbers as fractions.
No.
So if I can write a number as a fraction or a whole number, it's rational. If I cannot, it's irrational or complex. But right now we're not dealing with complex yet. So this says that if there's a rational zero to this, then its numerator must be a factor of 10. Because of this. And its denominator must be a factor of the coefficient of the highest term, which in this case is 1, plus or minus 1. Notice why it's plus or minus on every term, because minus 10 times minus 10 is also 10. Minus 10 times minus 1 is also plus 10. So this would tell me that my possible factors are these four numerators, and only those.
Yeah.
So if I'm trying to find the zeros of this thing, I have to start testing all of these and see which one works. And that's what finding zeros of cubics is a lot about, is a lot of trial and error. You'll never get more than one problem on a test because each problem might take 20 minutes. They are really tough, and who knew that it was so hard to find a rational factor? Well, let's say I wanted to see if any of these were rational factors of this. Well, I would use synthetic division. I would start with the easiest one, which is 1.
Yeah, and then you have to
see if you get a 0. No 0 there. So 1 is not a solution. About minus 1.
No.
Minus 1's not a solution. How about 2? Oops.
1, 2.
2 is not a solution. This is the process. Believe it or not, this is the way you have to do it.
Yeah, you have to do 8 problems.
Yep. These are brutes.
No.
Now, when you test some of these, you can tell a lot about what the possible answer is. Remember when I talked about upper and lower bounds? Well, if all of my answers alternate like that, that means that's a lower bound. That means there's no point in testing minus 10 or minus 5. Because minus 2 is the lowest possible answer we could ever have. If all of these have positive signs in front of them, then it's an upper bound. And we can eliminate the need to test some of the upper bounds. Now, since I made this up, I'm not sure any of these are a solution. Let me plug it in real quick to Wolfram Alpha. See what I find for solutions. Hold on. So x cubed minus x squared plus x. X cubed minus x squared plus x, was it plus 10?
Yeah.
Beauty of Wolfram Alpha is it shows you what you put in, which is nice. Your calculator doesn't do that. So notice it should be giving me the solutions here shortly. It also gives you the zeros. And here's our zeros. Approximately negative 1.73. Well, that's not a rational number. That is an irrational number. Okay? So this particular problem that I made up off the cuff has this as one real solution, as an irrational solution, and it has two imaginary solutions. You've probably discovered by now that all imaginary solutions come in pairs. So if you have an imaginary solution to something, you must have the conjugate also. So this didn't have a rational solution. So none of these are going to work because there was no rational solution. And all right. What else you got?
Let's see if this textbook that we figured out has flaws. Can you give us one? 3x to the fourth plus x cubed minus 4x squared plus 9x minus 3 divided by x plus 5.
Okay. What are we going to get when we divide that? Assuming this is a solution. And
you're going to get a cubic.
Exactly. So we're still not going to be able to solve it very easily. But we can start. Well, we can see if this is a solution. And if that is a solution, then this will yield a 0 as the last number. Okay, do it for me.
3, 15.
Minus 15?
Oh, minus 15, yeah. And then 14.
Minus 14?
Yeah.
You need the sign. The sign is as important as the number is. If you don't have the sign right, you're not getting it right.
And then minus, 70, 66, 330, negative.
Well, clearly that's not a solution either. It's not equal to 0. So I don't know why they keep giving you these problems where they're not solutions. That's a little bizarre. Are you getting these problems from chapter 2?
Yeah, chapter 2.4, the exercises.
All right, let me turn to that. That's where I'm at. It's 2.4. Let's see if I can find the one you just gave me, because I bet it's in here. Yeah.
In my book, it's number 10.
I got it. Mine's number 10 also. Divide using synthetic division and write a summary statement in fractional form. All right. So I guess I needed to do this last step here. That's minus 1605. It's plus, actually. So the remainder is 1602. So when you divide this polynomial by this linear factor, what is the solution?
The solution is 3x cubed minus 14x squared plus 66, plus 66x minus 321 with a remainder of 1602 over x plus 5.
Right. That's your summary statement. All right. Let's skip to 19. We need to do some where we actually do have a solution. Is this your 19?
Yeah.
Okay. And they want to divide that by x minus 1, so I put 1 in there. I got 1 minus 1, 1 minus 1. So let's see if this is a solution. 1, 1, 0, 0, 1, 1, bingo, 0.
Yeah.
So, the fact that we got 0 means x minus 1 divides into that evenly. So that's one factor. And the other factor would be what?
X squared plus x.
Plus 1. This 0 means the x coefficient is 0.
Yeah.
Okay? And notice that if I FOIL these two together, I get x cubed plus x minus x squared minus 1. That's exactly that.
Yeah.
Okay? Let's try a little harder one. Let's try 23. So across the top we got 4, 9, minus 3, and minus 10, and there's no degrees missing. We got a cubed, a squared, an x, and a constant. So I don't have to concern myself with putting in any zeros there. We're dividing it by x plus 2. So let's see if this is a factor of this polynomial. So what are these numbers?
It's 4, negative 8, 1, negative 2, negative 1,
Whoops.
negative 2.
Hold on. Add negative 3 and negative 2.
Oh, yeah. 5. So that is.
Problem with synthetic division is that you have like 10 calculations to make. And if you make one of them wrong, you're not going to get the right answer.
Yeah.
So it really requires perfection. And this means that the resultant factor is, let's see, this was a cube, so this is 4x squared plus x minus 5. Now, as to whether this factors or not, they didn't really ask us to do that. They just said determine if it's a factor. Let's do 24. 24 looks pretty interesting. 24, I've got a minus 1 there. Is your 24 this 2x to the 10th?
Yeah.
All right, so there's my 2. Tell me what to write across the top.
2, minus 1, 1, 1, plus 2, or 2, 2, and 0, 0, 0, 0, and
Need a 0 for each missing x. We have an x to the 5th missing all the way down to x to the 1. So we need 5 zeros and a minus 3. Okay?
so it's going to be 2, negative.
First of all, are the bets favoring or against that this is going to work?
I have no idea.
It's going to work, I guarantee it. Without having done it. They wouldn't put it in there if it didn't work.
Well, yeah.
That's the reason I think it'll work. It's because there's no reason to put this very strange problem in here if this was not a solution. So, let's see. I might be surprised. Tell me the numbers here.
2, -2, -3, 3, 4, -4, -3, 3, 3, -3.
Hold on. What's this one?
Oh.
That was +3, so now 2 plus 3 is 5.
Yeah, I don't know.
Did I make a mistake, or am I right?
No, I shifted my thing over a little bit.
Okay.
So it was 2, 3, 5.
Okay, now what goes here? -5.
-5.
-5.
-5.
5, -5, -5, -5, -5, -5, -5. I was wrong. It doesn't.
Yeah.
Okay. Well, it still shows us that we can do it. And the answer would be, oddly enough, 2x to the 9th minus 3x to the 8th. In other words, the answer has every degree. And that's quite common. Minus 5x to the 4th plus 5x to the 3rd minus 5x squared plus 5x minus 5. With the remainder of 2 divided by x plus 1.
Now that's a very large equation.
Yes, it is. I couldn't figure out why that was in there because none of the others are anywhere near like it. Actually, 22 is a little bit like it. Let's do 22. We're dividing x cubed minus 3x minus 2 by x minus 2. Okay, so what goes in the box?
2.
What goes across the top?
1, 0, -3, and -2.
Okay. 1, what goes here? Lucas, what goes here?
2.
Here?
2. 4 and 1 and 2 and 0.
Okay, so our summary is x minus 2 times
the x squared plus 2x plus 1.
That's it. Now, factor that fully.
That's x minus 2, x plus 1 squared.
Yeah. Okay. So let me take a look at the rest of this chapter here. Is your 25 based on a graph?
Yeah.
So, let's do that. Let's estimate or guess the possible linear factors
Um,
based on the graph.
would it be, I don't know, I would say x plus 3, x minus 1, and x minus 4.
Yeah, that really looks like it goes through like 3.4.
Oh, yeah.
So that last 0 is probably not rational.
Mm.
It looks like it would be irrational. And notice that the two rational answers we came up with do indeed fit the rational factor theorem. In other words, 3 is a factor of 51. It's 51 is 3 times 17. And of course 1 is always a factor, so in other words, if we had to use the rational factor theorem on this, we'd have 51 times 1, we'd have 17 times 3, both of those in the numerator, and 5 in the denominator. So our possibilities would plus or minus 51 over 1, plus or minus 51 over 5, plus or minus 17 over 1, plus or minus 17 over 5, plus or minus 3, plus or minus 3 over 5. Notice that all of those are rational. And 2 of them worked. The 3 worked and the 1 worked. I should say the negative 3 worked and the positive 1 worked. And then the beauty of cubics is if you can come up with one solution by however method you have to do it, even if it takes 20 minutes, well, now you divide that solution into the cubic and you're left with a quadratic, and you can always handle a quadratic. So the secret to these high degree polynomials is chopping them down one at a time. If they gave you a quartic and said to you that 3 plus I was one solution, complex solutions always come in pairs, never alone. There's no way that can be the only complex solution to a polynomial. If 3 plus I is a solution, then 3 minus I is also a solution. Now, if you start with a quartic and you synthetically divide it by that, you'll get down to a cubic. And then you synthetically divide it by that, you'll get down to a quadratic. And then you can use the quadratic formula. So they give you lots of problems like that, where they'll give you a quartic or a cubic, and they'll give you an imaginary solution, and they'll say, find all the solutions. And that's the way to do it. Now, do you know how to divide synthetically by an imaginary number?
No.
Let's do one of those. I'm looking for one. I'm going to make it easy. Have you even gotten to this yet? You may not be on. This is 2.6 in my book.
No, I don't think we have talked about that.
All right. Well, let's hold off on that then. Before we go there, I don't want to get you way ahead. I mean, I don't mind you getting ahead as long as you're doing A, work on what you're covering now, but only if that's the case. let's see, let's go back at the end of 2.4 and have another look at this. Let's look at some of these higher problems, like 27. Do you have to do any of these?
The degree 3, we have gone over that some.
Let's do 27.
Okay, so
They want the polynomial with a leading coefficient of 2 that has given degree and zeros. So what are my factors? What are my linear factors?
I don't actually have that question in my book, so.
Okay. They tell us that these zeros are -2, 1, and 4.
Yeah.
Okay, so what are my linear factors?
There'll be x plus 2, x minus 1, and x minus 4.
Okay, so now let's figure out what polynomial, in other words, I'm going to make that equal to 0. Now let's multiply all these together and see what we get. Multiply the first two.
X squared plus x minus 2.
Okay, and then multiply that by this binomial.
That would be x cubed minus 4x squared plus x squared minus 8, or x.
Hold on, we forgot this term times this term.
Which term?
We forgot that middle term times the last term. In other words, when you're multiplying these, you always want to do it in a methodology that's the same. You don't want to deviate.
Yeah. So that would be minus 4x plus 8.
Hold on. Now we got to go back and do that times that.
Wow, this is like so longer than I thought it would be. Alright, so, and then...
Let's talk about this, because I'm not sure how much of this you've done. Have you done much of multiplying trinomials by binomials?
We did one problem.
Notice that FOIL doesn't do much good.
No.
But ET does. And ET stands for every term times every term.
Yeah.
That's all you have to do. I don't care if I have 3 terms times 7 terms. I'm taking the first term, multiplying it by all 7, taking the second term, multiplying it by all 7, and so forth and so on. And always follow a pattern. Don't jump around. Don't multiply that times that and then decide to multiply that times that and then try to multiply that by that. You'll never remember what you've done and what you haven't. So always do the first term times that. First term times that, second term times that, second term times that, third term times that, third term times that.
Yeah.
Now, let's simplify it.
It's x cubed minus 3x squared minus 6x minus 8.
Plus 8, I think.
Oh, yeah.
Okay. So there's our polynomial, but what's missing? Because they said we need a polynomial with a coefficient of 2 on the highest degree term.
Then we need to, we should have
multiply everything by 2.
Yeah.
Notice what happens. We get 2x cubed minus 6x squared minus 12x plus 16, and we multiply the right side of the equation by 2, we still get that. So this polynomial is not the same as this polynomial. Be very clear about that. They are different. But they both have the same zeros. In other words, one of those polynomials might look like this.
Yeah.
The other might look like this.
Yeah.
Same zeros, different function. And that's something that is kind of an important concept to really get in these polynomials, is that just because it has certain zeros, that's all that means, is it has certain zeros. When I multiply those factors together, I get this polynomial here, or rather this one here. But I can have any multiple of that I want. I can multiply that by 10, because when I multiply the right side, I still get 0. So even if I multiplied it by 10, the resultant polynomial would still have these same 3 zeros.
Yeah.
All right. I'm looking at some of these other problems here. Let's look at my 33. Fairly straightforward problem. It says use the rational zeros theorem to write a list of all potential rational zeros. I think they mean the rational factor theorem. And then use the rational zeros theorem to determine which one, if any, are actually zeros. So what are my, in other words, if they gave you this and they said factor it, there's really only one place to begin if you don't have a calculator.
Yeah.
That's with the rational factor theorem. So what are my list of all possible numerators?
They would be -1 and 1.
These are always plus or minus. Yeah, -1 and 1, plus or minus 1. No matter what number I put, it's always going to have a plus or minus sign in front of it. Okay? What are a list of all my possible denominators?
Plus or minus 2, plus or minus 3, plus or minus 1, and plus or minus 6.
So now, what are a list of all my possible rational zeros?
Plus or minus 1/2, plus or minus 1/3, plus or minus 1, and plus or minus 1/6.
Good. And that's what you do. And now, if I want to test some of these, when it comes down to the trial and error part of these problems, I always use the thing that's going to be the easiest to do. In other words, I'm going to start with +1. And just go through each one of them. Bingo. First one worked. So 1 is a solution.
Yeah.
What is my, now where am I at? In other words, that's huge. Because now I have a linear factor times a quadratic factor. So my linear factor is what?
X minus 1.
And my quadratic factor is?
6x squared plus 6x plus 1.
Okay. And does that factor easily?
Yes. It's
I don't think it does. 3 and 2 don't work.
Oh, that's true. I was thinking if the
So if I plug that into the quadratic just to see whether we even have imaginary solutions or not, I get minus 6 plus or minus 36 minus 4 times A times C, which is 20, whoops, yeah, it's 24, all divided by 12. Well, that's minus 6 plus or minus root 12 over 12. That's minus 6 plus or minus 2 root 3 over 12. So we do have rational. That's minus 1/2 plus or minus 1/6 root 3. So our three solutions would be, what was our first one? X minus 1. So it would be x minus 1 times what? They're not complex. They're real.
it would be x. Well, okay.
Treat these just like that's a number. In other words, we're going to put a minus in front of it. I'm going to put parentheses around it, and that's a minus 1/2 plus 1/6 root 3. The other one is x minus a minus 1/2 minus 1/6 root 3.
Yeah.
Now, when we simplify by removing the parentheses, we get x plus 1/2 minus 1/6 root 3. Over here we get x plus 1/2 plus 1/6 root 3.
Yeah.
And that's the way to write your solution, believe it or not. That's the final answer. And that's how you handle irrational solutions. That's irrational. In other words, any number that's the square root of something is irrational unless it's a whole number. In other words, square root of 16 is rational because that's 4. But square root of anything that does not convert to a whole number is irrational.
Yeah.
All radicals are irrational unless they convert to an integer or a fraction. In other words, I suppose the square root of 9/4, that's rational because it's 3/2. But the square root of any number is irrational. All right. Well, that was pretty good stuff to cover there. This is actually some of the harder stuff you're going to run into in pre-calc. This chapter in particular, I would say, gives most of my students the most trouble. Lucas, I will talk to you next Wednesday Wednesday at 3.
All right.
All right. Bye-bye.
Bye.